So to figure, now, polarity molecules can be really, really complex. We're going to simplify it down to some really, really simple steps and rules, okay? Later on in college or whatever, you may have to learn some more complex things about polarity. But we're going to simplify it as much as we can just to give you a very, very brief introduction to polarity of molecules. It's important to understand polarity. For example, water is a highly polar molecule. Oils, on the other hand, are very nonpolar. Why does water and oil not mix? Because one's polar and one's not. Okay? Polarity has everything to do with the reason that you exist as something more than a puddle on the floor. Because if it weren't for the polarity of molecules, your cells would all dissolve in the water and you'd be a puddle on the floor. Okay? Huh? So polarity is really important. For a molecule to be polar, and only molecules are polar, well, for now let's leave it at that. There's always exceptions, okay? For a molecule to be polar, it must have two things, okay? One, it must have polar bonds. Two, it must have an uneven arrangement of those bonds. I'm glad you asked that question. I'm going to tell you what a polar bond is. First of all, I'll answer your question straight up, but you won't understand the answer until I explain it. Okay? So just hold your questions until I get to explaining it. Okay? Polar bonds have an electronegativity difference between 0.5 and 1.5. Okay? But, of course, you don't know what an electronegativity difference is yet. So we're going to get to that. All right. But we are going to need this reference right here. Remember in Unit 2 when we learned about the pattern of electronegativity? Yeah. Well, now you're going to use it. Here you go. Get that periodic table out. So let's look at water as our example. I mentioned water a moment ago. In this class, we've already learned to figure out the shape of a water molecule. We found that the hydrogen in water has 1 electron dot to share. Oxygen has 6 electron dots to share. These are the valence electrons, and it wants to have a full valence to be more stable. Hydrogen only needs 2, so if it shares 1, it's now more stable. I need 1 more hydrogen, hence H2O. Now both these hydrogens have 2 electrons, and the oxygen in the water has 8 electrons, making it more stable. Both of these now have the electron structure of a noble gas. Taking this, then I go to the Lewis dot formula. And then from the Lewis formula, I can start figuring out a 3-dimensional arrangement of the molecule. We start with what's called the electron dot shape. Okay, or the electron pair shape. Okay, so what we need to do is to figure out how many sets of electrons do I have around the central atom. Well, I have 4. If I have 4 sets, I must have a tetrahedral electron pair shape. If I have 4 sets of electrons around the atom of interest, the one that is linked to everything, the one that's the center of everything, I have to have a tetrahedral arrangement. If I have only 3 sets, I need a trigonal planar arrangement. If I have only 2 sets, I need a, what's it called? Linear. Okay? We did all these, but I'm reminding you now. Okay. So if I have a tetrahedral arrangement, then I need to have a set of electrons going in 4 directions three-dimensionally. Okay, and these are going to be 109.5 degrees apart. So I've got a set going here, a set going here, a set coming out toward you, swinging out away from the paper toward you, and a set swinging back behind the paper, back behind everything. All of these are 109.5 degrees. This is a tetrahedral electron pair shape. From the tetrahedral electron pair shape, then, I'm going to put atoms on shared pairs of electrons. I only need 2 atoms because I only have 2 shared pairs. So I'm going to put a hydrogen on this pair and a hydrogen on this pair. The lone pairs are still out here. Okay? This is a modified electron pair shape. It's still tetrahedral because I've got 4 things extending off the center there. This is a tetrahedral electron pair shape, a tetrahedral modified electron pair shape. The last stage of figuring out the molecular shape is to redraw this exact same drawing without the lone pairs. You have to use the lone pairs to see that we end up with this bent molecule. Okay? So this is a bent molecular shape. This is an uneven arrangement of bonds. If I have an even arrangement, I'd have hydrogens on all 4 of these arms. Okay? Uneven means it's not equally spaced around the central atom. This is equally spaced. This is not. Does that make sense? Here's a clue. If you have lone pairs, you probably are going to have an uneven arrangement. Got it? It's not absolute. It's not the only answer. But generally speaking, if you have a lone pair that you're going to have to remove from the final shape, it's going to be an uneven arrangement. Okay? All right. What we need to figure out now is what is the END. The END is the electronegativity difference. What does that word difference mean in math? Subtract. We're going to subtract the electronegativities. It's real simple. Just going to subtract the electronegativities. Find the electronegativity of oxygen, find the electronegativity of hydrogen, and find the difference. So, Drell, this means you. Kyle, this means you too. You would. There is no unit. It's an assigned value without getting too complex. There's no units for electronegativity. Yes. Well, they're going to be the same, right? They would both. You need both electronegativities, yes, but you only have to do the math one time because it's the same kind of bond. Does that make sense? No. We've only got a bond between oxygen and are you asking us to subtract both hydrogens from the oxygen? No. All we need to know is the electronegativity for this bond, and then we need to do the electronegativity for this bond, but they're the same. So you only have to do the math once. Does that make sense now? I misunderstood your question. I'm sorry. Okay. The difference in electronegativities. Exactly. So oxygen's electronegativity is 3.44. And hydrogen's electronegativity is 2.1. And if we subtract 2.1 from 3.44, we get 1.34. That's the electronegativity difference for an oxygen to hydrogen bond. But we have an empty slot over here. So back in Unit 1, we began learning that you're supposed to round those off. Somebody asked that question a minute ago, and I said yes. So the electronegativity we actually want is 1.3. Question: is that electronegativity difference between 0.5 and 1.5? Yes. Therefore, this bond is polar. The bond is polar. We've met this criteria. We got polar bonds. We have an uneven arrangement of bonds. We've met both criteria. Therefore, this is a polar molecule. Does that make sense? Don't make it hard. You just got to find the electronegativity difference, see if it meets the criteria, plug it in to find your answer. Okay? 2 criteria. Oh, sure. Why not? That'd be fabulous. The electronegativity. That's what difference means, right? I mean, I'm not trying to be sarcastic. I'm just saying, reminding you, just that's what, trying to clue you into the term actually applies. It's like a math term. Determine if CO2 is polar or nonpolar. What are the 2 criteria you need to make it polar?
It has to be the electronegative difference thing has to be between 0.5 and 1.5.
Okay.
And it has to have uneven arrangement.
Okay. Is it uneven arrangement? You don't. It sounds like some of you think you're sure, and some of you don't know if you're sure. Okay. So if I've got 2 sets of electrons, y'all aren't listening. I got 2 sets of electrons around the atom in the middle of everything. Okay? 2 sets of electrons, as far apart as I can get them in 3-dimensional space, is what degree angle?
180.
180. That's a straight line. I can't get them any further apart than that. Okay? The next step, then that's actually our electron pair shape. And if I then plug atoms on that structure where I've got sets of electrons, Dara, line, 00. Does that look like an even arrangement or an uneven arrangement? Even. Since I have to meet both criteria, and I haven't met this one, nonpolar. Okay? You didn't even have to calculate the electronegativity difference if you didn't want to.
So what is polar?
The electronegativity difference for a carbon to oxygen bond is 0.89. That's a polar bond. But the molecule is nonpolar because it's not an uneven arrangement.